Thank you. We hope you're all having a great afternoon. So we are the representatives of the Thayer Energy Club. I'm Vanessa, I'm the club's president. This is our VP and another member of the club. We are the newest student-run organization on campus, and we have been working with the coordinators of the Jones Seminar to arrange the visit of today's speaker, Tony Barbagallo, who we hope will provide a slightly different perspective than some of our past Jones speakers. By the way, did you know this is the first Jones Seminar ever to be coordinated by students? It's almost shocking. Aside from doing speaker coordination, the Thayer Energy Club, or TEC for short, also holds biweekly lunch meetings bringing together the students and faculty of Thayer to discuss a variety of topics in energy. Every lunch includes a brief presentation from a guest speaker on some topic in energy, followed by a discussion. Our next lunch will be on the 18th and will feature a presentation by Dr. Marie Munster of the Technical University of Denmark on her work modeling large-scale energy systems. If you're interested in coming to one of our events or to be put on our email list, please email us at thayer.energy.club@dartmouth.edu or come and find us after the talk. And now, the reason we're all here, to learn more about cow manure. But seriously, we are honored to have today with us Tony Barbagallo, an industry expert on solid waste management and a construction manager for Vanguard Renewables on the largest on-farm anaerobic digester in Vermont. Tony is a registered engineer with over 30 years of work experience in project development and construction with an emphasis on organic waste management. Previously, he spent 7 years as Director for Development for Casella Organics and 20 years as a facility manager for Vermont's Chittenden Solid Waste District. He holds a BS in Civil Engineering from Clarkson College of Technology and an MBA from University of Vermont. Let's give a hand for Tony.
All right, well, thank you. Can everybody hear me okay? It's a pleasure and an honor to be here, and I am here today to talk about anaerobic digestion at the Goodrich Farm. It's a project that Vanguard Renewables was constructed and began operation about a year ago, and we're going to get into some detail on that. But first, I was advised that before I get into the project, it'd be nice maybe if I talk a little bit about the ARC career and some past projects I've been involved in. So that's what this is right here. From New Jersey originally. You might pick that up in my accent or my attitude. Left Jersey, went to Clarkson to become a civil engineer. Got a degree in bachelor's in civil and environmental engineering. Then I went on to UVM for a master's in business administration. Fell in love with Vermont and essentially really never left. For work experience, I started off in the construction industry. My dad was a small contractor. I was running heavy equipment before I had my driver's license. Went through a series of summer jobs, getting more immersed into the civil engineering field. When I graduated from UVM, I went to work for Pizza Galley for a short time and then got into the consulting world. It was when I was with Donald Hamlin Engineering that I started getting into more environmental projects and decided that I wanted to go that way with my career, and then moved into solid waste from there on out. And I've been in solid waste for about 40 years, and I'll go through a little bit more of that as we move on. So to start with, just some past projects I've been involved with. When I first graduated from college, I went to work for Pizza Galley Construction, now known as PC Construction, and we were building the maximum security prison addition to the Concord, New Hampshire State Prison. So that's what's circled in here. You can see it's kind of a more progressive design than your typical prisons. Moving on from there, I moved into consulting engineering and was designing subdivisions for a bit. And while with Hamlin Engineering, I started working on landfills. I was the young engineer in the office, and nobody else there wanted to work on landfills. They were all just it was too dirty for them, essentially, so it became my job, and I would be out sampling groundwater at landfills. And back in the day, these were unlined landfills, so there was no plastic liner beneath them. Any precipitation that wet the trash eventually made its way to groundwater. And from sampling these groundwater wells surrounding landfills is when I had my environmental gestalt and decided that I wanted to dedicate my career towards helping the environment instead of building subdivisions, essentially. I went on to work for Chittenden Solid Waste District for 20 years. I was facilities manager there, planned, designed, and built a lot of different solid waste facilities. This one here, shown in the red circle, is a materials recovery facility. It's where most of the recycling in Vermont goes to be processed. And I gave you this overview here just to show you that you can put a solid waste facility in a relatively developed urban area if you have the proper controls about it. And this facility is a success. It's been operating for probably close to 30 years now through different iterations and generations successfully. And it starts off, it is now a single stream facility, and material all comes in and gets dumped on a tipping floor and then gets pushed up a conveyor. And from there it goes through a long process that's too complicated to get into right now. But that mixed recycling goes in, and what comes out are these bales of material separated by commodity type that's then sold on the open market. And you can see different bales of cardboard and paper and plastics and tin there. Moving on, at Chittenden Solid Waste District, I also was responsible for the Intervale Compost Project, which was the largest composting operation in Vermont at the time. It subsequently has morphed into Green Mountain Compost, still the largest compost operation in Vermont at the time, still owned by Chittenden Solid Waste District. Moving on from Chittenden Solid Waste, I was also the Director of Business Development for Casella Organics, and while there I built an alkaline stabilization facility for wastewater treatment sludge. This is wastewater treatment sludge is a wastewater plant that gets human waste to it. The source system's empty there. And a byproduct of a wastewater plant is a sludge. It's a problematic material to deal with. This facility took that sludge, that dewatered sludge, and made it into a fertilizer product. It's in Chattagay, New York, right next to Canada. It was built in the middle of winter. So I threw a little slide up there to show that it's sometimes, and you got to think about these things. People don't think that, oh, wait, if I permit it in the summer, I'm building it in the winter, and that's not real. It happens a lot in Vermont or in the Northeast because permitting generally takes longer than you anticipate. And then that drops your project into winter construction and all the ordeals that entail. The center photo here is actually the reaction vessel in that alkaline stabilization facility. So we would take wastewater sludge, mix it with lime kiln dust, and put it into this reactor vessel where it would sit for several hours, and the pH and temperature would drive it up, so it was a pasteurization process. What came out the other end was a dried product that could then be land applied, and that's what that bottom photo is a manure spreader slinging the Fertilizer, which is the product brand. That's what we called the product that was made. So this is being applied to farmland up in Chattagay area of Vermont right now. And that's a quick overview of the arc of my career in a nutshell, if you will. And now I'm ready to move on to the anaerobic digestion project that you guys asked me to come speak about today. So I work for Vanguard Renewables. Vanguard has numerous digesters across the country now. It's a Massachusetts company. It has 6 digesters that are on farm that take cow manure and food waste and co-digest them both. It also has a number of other manure-only digesters located in the west and in the south and under construction. But I'm here today to focus on Salisbury since I was involved in the construction of that for the past 3 years. A little bit of an overview about Vanguard's farm-powered system first. The inputs and outputs. There's 2 inputs to the project, essentially. It takes the cow manure that's produced on the farm we're co-located with, and it brings in food waste from off-site. And it combines both of those in a co-digestion system. And what comes out the back end is a renewable natural gas, an excess of heat, some of which is made available to the farm for use in heating their buildings. We also come out with a digestate that uses a low-carbon fertilizer. And there's a lot of greenhouse gas reductions because we're taking these input materials that otherwise generally would have emitted methane into the atmosphere as they were naturally decomposing. A little bit more on the food waste side of things. So the food waste just doesn't magically appear at the anaerobic digester. Vanguard has to go out and secure that food waste through a supply chain. And we start off right at the generators of food and beverage companies. And we have staff that are out in the field contacting these people, getting them to sign up to participate in the program. We supply them with the bins that they will put the organics in. We arrange for the transport of those organics. Generally, within commercial establishments, a lot of those organics will be contaminated, such as their packaged products where they're beyond the expiration date, or they were mislabeled, or it was a bad run of Ben & Jerry's or something like that, and they didn't meet their quality control parameters. So things that are packaged can't go right to a digester. A digester can only accept liquid or semi-solid materials free from contaminants. So they go through this organics recycling facility, or a DPAC facility, as the industry calls it, first, and that's removes the packaging material so that it prepares it for acceptance at a digester. A little bit more on the DPAC facility. This is Vanguard's new facility that's in Agawam, Massachusetts, and you can see it takes packaged material there on the lower right, and we'll shred those packages up, separate the organics from the packaging, and the packaging will either be discarded or recycled if it can be, and the organics get pumped via tanker truck to the anaerobic digester. In the center photo there, you can see a bunch of kegs, beer kegs. Expired beer or off-product beer is one of our major feedstocks. It's very high energy, but you got to get it out of the keg. So this is a contraption we call an octopus that can empty a bunch of kegs at once. So benefits. Why do people participate in this program? It is a partnership, so we're co-located on a farm. So the farm needs certain benefits out of that in order to get them to participate. We have a lot of feedstock suppliers. We have to have a rationale why they want to participate. And a lot of that is driven by environmental benefits and community benefits that are not necessarily germane just to on-site at the farm or to that feedstock partner, but provides them with a lot of community incentives and goodwill and good PR in some cases. But a farm can drastically improve their environmental footprint. We'll get into that a little bit more further on in the slides. As far as feedstock partners go, I think this is the last slide I'm dealing with feedstock on, but generally people will participate in order to put that farm-powered logo on their press releases and such, and participate in the program. We have a lot of national manufacturers participating right now, and as time goes on, you're going to start seeing that farm-powered logo on actual beverage cans and such. So that's kind of our branding, if you will. For the Salisbury, Vermont project, the partnership included not just Vanguard and the Goodrich Farm, which it's located on, but it's the first project that Vanguard is producing a renewable gas on. All our other projects were producing a renewable electricity or power. For this project, we're upgrading the gas and going to a pipeline. So Vermont Gas Systems is one of our partners on the project. Also, Middlebury College has signed up to purchase the renewable gas that we generate, or not all of it, but a significant share of it, a small majority, I believe. So it takes a team to get these projects going generally. You got to have a good site, which is the farm. You got to have off-takes for your materials that you're producing, which in this case is Vermont Gas, but it could also be a power company if you're going to electric supply. And then you need a buyer for that electric power as well, or gas in this case. This is a little slide about farm facts on the Goodrich Farm, where we're located. They have about 900 cows, 1,700 acres of hay, 650 acres of corn. In the past, those acres all need to be fertilized. They're growing crops, so every year they're buying urea and other products to land apply on these fields to grow the crops. In the past, they've also been applying their liquid manure there too. Because we're bringing in so much more food waste, so keep in mind the project's 100 tons, the design capacity is 100 tons of manure a day, 180 tons of food waste. So we're almost tripling the volume of material that's going through their system. In the past, they just had to apply the manure. Now they've got to apply the manure plus the food waste. But through our process, and I'll get into this further on, because of the treatment of the manure and the food waste, they're actually able to apply all that extra material on their fields and decrease the amount of fertilizer they're buying and increase their crop yield at the same time. And meanwhile, we're generating 180,000 cubic feet, or MCF, which is 1,000 cubic feet of baseload renewable gas per year, putting it into a pipeline. A little bit about the site overview. So this is a photo of the site that is completed. And here's some of the various components of it. So I'll walk you through it quickly here. The farm cow barns are all in the back, in the background of this photo. All the manure flows is managed in a liquid manner, flows through slots in the barns, through trenches underground, all to one centralized pit where we have a grinder pump, and that's where we pick up the system. So the farm is responsible for delivering all the manure to a central point. Then it becomes our responsibility to manage. We pump it from the manure pit into the separator building where we dewater the manure, and the dewatered product is used for animal bedding. So the farmer gets all the dewatered manure. He uses it to rest his cows on. This is very common in the dairy industry. Not that innovative for us, but we added this component to it. We're responsible for separating the manure and providing the farmer with an animal bedding that's satisfactory to him. The liquid out of this separator building is pumped right to the digesters tanks, which are right here. Meanwhile, food waste comes onto the site and goes to the hydrolyzer, which is over here. There's a tipping area right here. You'll see later on a photo of it. That the material is tipped, goes into the hydrolyzer where it stays for a few days, then is pumped into the digester. So that's where the co-digestion comes from. We're digesting manure and food waste together. The site is off the power grid, so there is no electric run to the site. So we're generating all of our own heat and power through an 800 kilowatt combined heat and power system right here that runs on natural gas. There's a heating container next to it. In the event that the combined heat and power system is down, we can supplement or still run the facility by having our own boiler, and also over here is a backup diesel generator, so we do have backup power supply in the event that our CHP unit goes down for repairs or emergency downfall. What else? We produce methane out of the digester, which then goes to a gas upgrader, which is over here, which upgrades the gas to pipeline quality standards and injects it into the Vermont Gas Pipeline. We have an office container here, and you can see the site is pretty well modularized as we're trying to reduce our construction costs and decrease our construction time by putting as much as we can into these shipping containers or sea containers so that we can prefab them off-site and move them onto site for future construction of other projects. Moving on, a little bit of detail on pieces of equipment. So the first thing that happens is we separate the liquid manure from the solid manure, and that's what this equipment right here is. These are screw presses, and essentially they're a cylinder with fine slots in it and a progressive screw in the middle. Manure is put in at one end, and as that screw spins, it squeezes it and squeezes the liquid out, and eventually what comes out the end is a dewatered animal bedding product that the farm uses. And this is what that looks like. So manure comes in at 7% into these screw presses. This animal bedding here is about 47%, comes in at 7% solids. Sorry, I missed that one word, solids. This animal bedding is about 47% solids, so we're squeezing a lot of the water out. Still has moisture in it too, but 47% is actually a very high solids content for a dewatering, mechanical dewatering process to achieve. The liquid and semi-solid food waste that comes in, as I said, goes to a hydrolyzer. So that'll come in tanker trucks generally from off-site. And it'll back up to this hatch. And it's kind of a little hard to see in this photo, but this right here is a hydraulic lid that opens up into above this pit. So this is a pit with a bar grate over it so nobody can fall in. The truck will back up, the hatch will open, they'll hook up a little pipe, and they'll just discharge into this pit. If this is semi-solid material, if it's very liquid, they'll hook up here and just go into this little pipe right out here and avoid the whole pit. Sometimes we'll have 3 or 4 trucks dumping at one time, and there'll be a couple dumping into the pit at once. This right here is a shaft propeller mixer. There's 2 of them on the hydrolyzer. The hydrolyzer is a 500,000 gallon underground tank. It's an oval. It has a center wall in the center, so it's a raceway. The material goes around and around that center wall. This mixer has a propeller on the end, and that's what kind of pushes the material around and helps chop it up a little bit as it's going around too. Here's a shot of the digester under construction. So there's 2 1 million gallon digesters on site. They're cast in place concrete. They're 20 feet tall. Half of it is buried, half of it is above ground. And similar to the hydrolyzer, they're oval with a center wall, and you can kind of see the ovals going around here, and then this is the center wall. It doesn't connect. There's still an opening at both ends, so you get a racetrack that goes around and around. And the 2 propellers just push that material around. Stays in the digester for about 27 to 30 days. It's a mesophilic digester, so it operates about between 100 and 104 degrees Fahrenheit. On top of those concrete walls, we put a roof, and it starts off by laying timbers across. So these timbers will go all the way down. They're just being installed here. Then on top of those timbers, we put an elastomeric membrane, and that's put over the whole digester. It's sealed around the edge with an airtight ring, essentially, to keep the gas from escaping. And that membrane will blow up and contract as the gas fills and is captured and released from and used. Also, there's a net that's used. So the elastomeric membrane really doesn't have any structural capacity. So to keep it from overexpanding, we put a polypropylene net on too, and that's really what contains the gas bag from overexpanding. This is what it looks like when it's done. You can see that the methane bags are inflated here. It's a low pressure system, so at maximum, the maximum pressure we'll have in these digesters will be 4 psi. Anything more than that, and there'll be automatic venting that goes in place. And there is a flare, so if we cannot use the biogas to upgrade it, the gas gets flared before it's released. The digestate out of the digester that is eventually used by the farmer goes through an intermediate process called dissolved air flotation to remove phosphorus. Vermont has a fairly large phosphorus problem, and a large part of that is being driven from runoff from farms. The state is under a federal directive to remove its phosphorus loading to Lake Champlain. So there's a lot of constraints being put on farmers these days to reduce their phosphorus loads. What we've done on this system, and this is rather innovative, there's not a whole lot of manure systems in the country that are removing phosphorus like this, but in order to allow the farm to spread more digestate, they needed to remove phosphorus. So they're, in the past, producing a manure, land applying the manure. How much they can apply is driven by the nutrient loading, nutrient uptake of the crops they're growing. So there's an agronomist working for the farm who's determining how many gallons every year of manure you can put on this acre based on what the soil currently has in it and what the plants are going to uptake. In the end, it's all being driven by phosphorus loads. So the farm was constrained from growing because it had no more land to apply more phosphorus to, essentially. By us putting in this phosphorus removal system, we reduced the phosphorus load in the digestate so that they could apply not only the manure they were already generating, but the additional food waste, almost twice as much as the manure volume, to their land and still meet phosphorus loading. So they get the benefit of the additional fertilizer or the nitrogen, which they like. It's cut down on their purchase of urea significantly. And they get the water, which they like too, because it's irrigation, which helps them. After the dissolved air flotation process, it goes to storage tanks. And these are there's 2 slurry store tanks on site. Each of them is 1 million gallons. Each of them is 2 million gallons. Those are 2 million, that's an error in that 1 million gallon tank. Those are 2 million gallons each. And then there's an additional 3 million gallons of off-site lagoons. So we have 8 million gallons of storage. The reason we have so much storage is because of the winter conditions. You're only allowed to land apply this digestate during periods when crops are growing. So we have to have enough storage to go the entire winter. And adding a safety factor, that's 6 months. So regulations require 6 months of storage, which is what we built. As far as the gas stream goes, gas comes out of the anaerobic digesters at 60% methane, CH4. You can't put it into a pipeline like that, though. You could burn it in an internal combustion engine and generate power at that concentration, but natural gas pipelines require about 97% methane. They also have a lot of other parameters that need to be met: moisture content, oxygen content. There's about 20 different parameters that we have to comply with. So this gas upgrading system takes that raw biogas and upgrades it to quality that is applicable to put it into the Vermont gas pipeline, and that's what we do. There's different types of technologies that can do this. This project uses pressure swing absorption to do that. You could also use a membrane system or an amine system. They all have different advantages and disadvantages, and I don't know that the industry has settled on one of those technologies yet. But out of this upgrader, which comes out at 97%, we go into the Vermont gas pipeline. And Vermont Gas, as a partner, I said, extended the pipeline 3 miles to get to this project, and then they installed a metering station right at the entrance to the project, and that's what this is. So this is Vermont Gas's system right here. The pipe comes out of this, goes directly to our upgrader, and we both have controls in place to measure what we're selling and buying so that we can agree. And it's been a very favorable relationship. This is Vermont Gas's first renewable gas project. So it's kind of a feather in their cap as well, and why, a good part of why they wanted to partner with us on it. As I said, the project is off the grid. So this is our 800 kilowatt combined heat and power system being installed. Again, it's a containerized unit. And this is run on natural gas. So we don't actually technically use the gas we produce on the site to burn in this. We take the gas we produce and we sell it as renewable natural gas. But we buy regular natural gas to run the equipment on, just because it's more economical for us to do that. Even though molecularly we are buying our own, using our own gas, because we're at the end of a pipeline, so anything we use is produced by us. I mentioned earlier, in the event that the combined heat and power system is down, we have a backup boiler, which is as small as this unit right here. That's all it takes to heat the digester, the hydrolyzer, and our buildings, and supply some extra to the farm. These are the heating headers here, so you can see we run heating pipes to the hydrolyzer and the digester, and how we do that is when we were building the digesters, we embedded PEX tubing in the concrete. So there's all these loops of heating lines in the concrete, in the floor and in the walls, both. And that's how we heat it. We insulate the outside of the tank, we heat the concrete walls, and let that heat the digestate. Other types of technology will put the heating elements in the digestate, but there's been problems with blinding and such with and corrosion with those systems, and this system uses buries it in the wall of the concrete actually. So the whole system is operated by a SCADA system, that's supervisory control and data acquisition. This is a schematic of the facility. You can see through icons, every piece of equipment is represented. Start off with the digesters are over here, but you start off with the manure coming in over here, goes to the separator building, right? That's the icons for that. And then it goes to the digester, the hydrolyzers over here. All of these pumps and motors are all able to be operated remotely from the operator's phone, actually. So the operator can run our entire system off of his phone. It's fully alarmed and notified. So if any of these pumps go out of any set parameters or any of the liquid levels go out of set parameters, an alarm goes off. The operators get that alarm on their phone, so 24/7 there's emergency response if something goes out of whack. The facility operates 24/7, 365. However, it's only staffed during working hours and on call if something goes wrong. So generally, just 5 days a week, 8 hours a day is staffing. There are a bunch of other mini or subsystems in that. They have their own SCADA system. For instance, the CHP unit has its own SCADA system. The biogas upgrader has its own SCADA system. The DAF unit has its own SCADA system. And you got to get all of these different components to work in harmony and talk to each other. So we have to take those SCADA systems, integrate it to our overall SCADA system so that everything's talking to each other and communicating and knows what everybody's doing. And we're also able to track trends to see where we've been. It helps you to see where you're going. You can identify your alarm history to find out where all your alarms are. That'll help you make improvements in focus where you need to make improvements in the future. SCADA systems are pretty essential these days. And this is a slide showing that the energy, renewable energy from food waste and dairy manure has much fewer carbon emissions than conventional natural gas or landfill renewable gas. These numbers come from the California Air Resources Board, which is probably the leading agency in the country doing this kind of metric. And it's a big driver for why we're going in this direction instead of producing electric power. In the past, most digesters produce electricity. Because of changes in the energy field, you're seeing less and less of that these days, and almost everybody is now moving towards upgrading their gas to going to a renewable natural gas, mostly because the economics favor that more than anything else at this point in time. I can go on, too.